Hello students, so in this lecture we are going to study kinetics of reversible first order reactions. So actually the reaction is first order reaction opposed by first order reaction. So we are going to study kinetics of first order reaction opposed by a first order reaction. So let us say reactant is A and the product is B. Kf is the rate constant for forward reaction and Kb is the rate constant for backward reaction. So the forward reaction is also a first order reaction and the backward reaction is also a first order reaction. So we write when time t is equal to 0 only A is present, only A is present and B is not present. So concentration of B we write here 0. At t is equal to t, some x amount of B is formed and amount of A present is A minus x. And at t is equal to t equilibrium, A minus xe, xe means equilibrium amount of product that is formed. So here it is xe. Now we write the rate of formation of P in forward reaction and rate of disappearance of B in backward reaction. So rate of formation of B through forward reaction we can write it as Kf multiplied by A minus x, which is concentration of reactant at time t. Next we write rate of consumption or disappearance of B in backward reaction. We can write it as Kb into x, because x is the concentration of reactant for backward reaction. Now the overall rate of reaction we can write it as dx by dt, because at time t the concentration of product is x and the concentration of reactant is also A minus x. So for when we talk about reactant, we talk about the rate of consumption of reactant. So if we take minus of d of x minus a minus x by dt, here the reactant is being consumed. So it becomes ultimately dx by dt, because A is a constant. If we talk about the rate of formation of bead, it also becomes dx by dt, because the concentration of B at time t is also x. So we can write net rate of formation of B which is dx by dt is equal to kf into A minus x minus kb into x. It is because B is being produced in the forward reaction and it is being consumed in the backward reaction. So net rate is this. Now at T is equal to T equilibrium, concentration of all reactants and products becomes constant and net rate of reaction is 0. So because net rate of reaction is 0, so we can write dx by dt, which is equal to kf into a minus x minus kb into x is equal to 0. So we have also x at equilibrium, x becomes xc, so we can write here a minus xc and kb into xe. So kf into a minus xe is equal to kb xe, or kf by kb we can write kf by kb is xe upon a minus xe, and kb here becomes kf into a minus xe divided by xe. So we put the value of kb in the rate equation, and then we will try to find the integrated rate equation. So our rate equation is basically dx by dt is equal to k into a minus x, kf into a minus x minus kb into x. So the value of kb that we are going to put here is kb is equal to kf into a minus x e divided by xe. From the previous slide we have found it. So kf into a minus xe divided by xe. So now dx by dt becomes kf into a minus x minus kf into a minus xe upon xe multiplied by x. So further simplifying, we write kf into a minus x into xe minus kf into a minus xe into x divided by xe. So when we break the parenthesis and further simplify, we get kf into a xe, kf may be taken as common, so kf may be kept as common, so it is a xe minus x xe minus ax plus x xe, minus minus becomes plus. So we plus x xe and minus x xe cancel each other. So now we are left with dx by dt is equal to kf into a can be taken as common, kf into a xe minus x divided by xe. Thus dx by dt is equal to kf into a upon xe into xe minus x. So now we integrate this equation using the variable separable concept of integration. Dx upon xe minus x is equal to kf a upon xe. All the terms are constant here, so we integrate dt, and here we integrate dx upon xe minus x. Now x is the variable here, and the derivative of minus x is minus of dx. So we put a minus here and a minus here. So now we get minus ln xc minus x is equal to kf a upon xc. Here f is a subscript, so into t plus c. Now at t is equal to 0, x is equal to 0, hence minus ln xc is equal to c. So c becomes minus ln xc. So putting the value of c in the equation, we get minus ln xc minus x is equal to kf a upon xc into t minus ln xc. Further simplifying the equation, we get ln xc upon xc minus x is equal to kf a upon xc into t. So this is one of the integrated equations for reversible first order reaction. We will further simplify it. So earlier we have seen kf upon kb is equal to xc upon a minus xc. So the equation here is ln xc upon xc minus x is equal to kf into a upon xc into t. So now we will further simplify this equation. So earlier we had kf upon kb is equal to xc upon a minus x. So now we get kf into a minus xc is equal to kb into xc, or kf into a minus kf xc is equal to kb into xc. So we get here kf into a is equal to kf plus kb into xc, or kf into a upon xc is equal to kf plus kb. So we are going to use this result in this equation. So our equation now becomes ln xc upon xc minus x ln xc upon xc minus x is equal to kf plus kb into t. So this is the final rate equation, or we can say this is the final equation for reversible first order reaction. A first order reaction opposed by a first order reaction. Now we will try to do some problems based on this. So our first problem is, we have a cis compound which changes to a trans compound which is in equilibrium with its trans form, and in both the sides the reaction is a first order reaction. The kf for this reaction is 3 into 10 to the power minus 4 seconds, and Kc is equilibrium constant is 0.1. So one point to mention here is also that equilibrium constant for reversible reaction, equilibrium constant Kc is equal to Kf upon Kb. This relation is also important and it is used in many numericals. So this question asks how much time is required for half of trans product to be formed. So the equation we are going to use here is ln xc upon xe minus x is equal to kf plus kb into t. So we have to calculate the time here. So whenever we are solving the numerical, we have to see the data given in the question, and then we have to see what we have to find, and then we have to relate the data given in the question with what we have to calculate. How can we relate them? So we can relate the data given in the question and the quantity we have to calculate using this equation. So now kf we know kf is equal to 3 into 10 to the power minus 4 seconds, and kc is equal to kf upon kb. Value of kc is also given, so kc is 0.1. So now we will use here 0.1 is equal to 3 into 10 to the power minus 4 seconds upon kb. Second inverse, sorry. Here it should be second inverse. So kb is equal to 3 into 10 to the power minus 4 second inverse divided by 0.1. So this is 3 into 10 to the power minus 3 second inverse. So we have kf, we have kb, and x is equal to xe by 2 we have to put. So now writing the equation ln xe upon xe minus x is equal to kf plus kb into t. Here x is equal to xe upon 2, thus ln xe by xe minus xe by 2 is equal to kf is 3 into 10 to the power minus 4 plus kb is 3 into 10 to the power minus 3, and both have units of second inverse and multiplied by time. So now here we have ln xe upon xe by 2 is equal to 3.3 into 10 to the power minus 3 multiplied by t. So here we have ln 2 is equal to 3.3 into 10 to the power minus 3 into t, or t is equal to ln 2 by 3.3 into 10 to the power minus 3. So ln 2 is 0.693 divided by 3.3 into 10 to the power minus 3. So here the answer is 210 seconds. We will do another question based on the same concept. In this question we have a reaction, we have a reversible reaction A to B. Kf is the rate constant for forward reaction, Kb is the rate constant for backward reaction. Here we are given B equilibrium, ratio of B equilibrium upon ratio upon concentration of A equilibrium, which is equal to 4. Kf is equal to 0.01 second inverse. Initial concentration of A is 0.01 molar and initial concentration of B is 0. Now we have to find here the amount of B formed after 30 seconds. Calculate amount of B formed after 30 seconds from start of the reaction. So again we have to use the same formula. We have B ratio of concentration of B equilibrium to A equilibrium, which is again Kc. So we have to again use the same formula. ln xc upon xc minus x is equal to kf plus kb into t. Here we have t. Now in this question we have to calculate x. So to calculate x we need the value of kf, we need the value of kb, and we need the value of xc. We have the value of t. So kf is equal to 0.01 second inverse B equilibrium upon A equilibrium is equal to 4, which is nothing but Kc. So thus we have Kf upon Kb is equal to 4. We know the value of Kf. Kf is 0.01, Kb we don't know. So here Kb we will get here is 2.5 into 10 to the power minus 3 second inverse. So we know the value of Kf, we know the value of Kb now. Now the only value that we need now is Xc. So Kf upon Kb is equal to Xc upon A minus Xc, we know this. So Kf upon Kb is equal to 4 and Xc we don't know, we know the value of A. Initial concentration of A is 0.01 minus Xc. So we have here Xc is equal to 0.04 by 5 is equal. So we will get here 8 into 10 to the power minus 3 molar. So now we have the value of Kf, we have the value of Kb, and we have the value of Xc. So we can proceed to calculate X. So ln Xc upon Xc minus X is equal to Kf plus Kb into T. So here we will say 2.303 log of Xc upon Xc minus X is equal to Kf is 10 to the power minus 2. We can write 0.01 as 10 to the power minus 2 plus 2.5 into 10 to the power minus 3 into 30, or log of Xc by Xe minus X is equal to, here we have 12.5 into 10 to the power minus 3 into 30 divided by 2.303. So after simplification we get this quantity to be log of Xc upon Xc minus X is equal to 0.163. So Xc upon Xc minus X is equal to 10 to the power 0.163 is equal to 1.455. Now when we simplify, we get Xc is equal to 1.455 Xc minus 1.455 X. So or X is equal to 0.455 divided by 1.455 into Xc. Now we know, put the value of Xc and we get the value of X. So when we put the value of Xc, which is 8 into 10 to the power minus 3, 455 by 1.455 into 8 into 10 to the power minus 3, we get 2.5 into 10 to the power minus 3 molar. So we have solved our second question also. So in this lecture we have done the kinetics of reversible first order reaction and we have solved two problems. So that's all for today.